Okay, so power series. Power series is a type of series where you have a variable x in it, and it kind of makes a polynomial with the leading coefficient, the first term, the coefficients being sequences. So if you take a look at the power series example, it's a sequence centered at C with just x to the first term, x to the second term, x to the first, x to the second, x to the nth, and it goes on forever. There are different ways to find radius and interval of convergence. For this class, you're only going to need to use ratio test or geometric series test, but mostly ratio test for most power series that you'll end up on. Anyways, you also have to test the endpoints if necessary when you are doing radius and interval of convergence. So let's do an example because it's hard to explain how to find radius and interval of convergence unless we're doing an example. So here's your first example. N equals 1 to infinity, negative 1 to the n, x minus 5 to the n over n2 to the n. And I'm just going to fix this really quick because it should say right here n plus 1. Okay, so let's go on. We start with ratio test. Ratio test says that things will converge if the limit as n goes to infinity of a of n plus 1 over a of n, absolute value, is less than 1. So let's go ahead and start with ratio test. Negative 1 to the n plus 2, x minus 5 to the n plus 1 over n plus 1, 2 to the n plus 1. Multiplied by the reciprocal of the original series, and then let's simplify. So the 2 to the n and 2 to the n plus 1 cancel out, leaving 2. The x minus 5 to the n and x minus 5 to the n plus 1 cancel, leaving 1x minus 5 on the top. The negative 1's cancel, leaving 1x negative 1 on the top. And so we have limit as n goes to infinity of absolute value negative 1 x minus 5 times n over n plus 1 with a 2 in front. So if you look, the numerator has an exponent of 1 and the denominator also has an exponent of 1 for n, and we're finding as n goes to infinity. So we do the leading coefficient over the leading coefficient. The leading coefficient of n in the numerator is x minus 5. The leading coefficient of n in the denominator is 2. So we have x minus 5 over 2. And if it's going to converge, this should be less than 1. So we set it up. Negative 1 is less than x minus 5 over 2 is less than 1. Solve for your x, and we get 3 to 7. So on a number line, here's 3, here's 7. Halfway in between is 5. You can also get the 5 from the x minus 5 where it's centered at. But the distance from 5 to 3 is 2, and the distance from 5 to 7 is 2. So your radius of convergence is going to be 2. Now, we also have to test the endpoints before we can state our interval of convergence, because we don't know whether it actually converges at 3 or at 7. Because remember, for ratio test will only tell you if it converges if it's less than 1, or it diverges if it's greater than 1. It doesn't tell you anything if it equals 1. So you have to do another test. So if x equals 3, then the sum from n equals 1 to infinity of negative 1 to the n plus 1, and plugging in 3 in for x, then simplifying, n 1 to infinity, negative 1 to the n plus 1 times negative 2 to the n over n2 to the n, you can split up the negative 2 to the n to be negative 1 to the n times 2 to the n over n2 to the n. And then 2 to the n's cancel. And then you can combine negative 1 to the n plus 1 and negative 1 to the n into negative 1 to the 2n plus 1 all over n. This 2n plus 1 is always odd, so it doesn't alternate. It stays negative 1 in the numerator all the time over n. So this is going to diverge by the harmonic series test. Now, if x equals 7, the sum from 1 to infinity of negative 1 to the n plus 1 with a 7 plugged in for x, 7 minus 5 to the n, over n2 to the n, those cancel. So you have negative 1 to the infinity, or negative 1 to the n plus 1 all over n. This one does alternate, it does decrease in magnitude, and the limit equals 0. So this series converges by the alternating series test. So in interval, our interval of convergence is going to be 3 is less than x is less than or equal to 7. 7 is equal to because it converges, 3 is not equal to because it diverges. That's example 1. That's the hardest one, when you have an interval and you have to test the endpoints. Other intervals of convergence will be a lot easier, so let's do another example. Example 2. Sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Doing ratio test first. Don't forget, when you plug in n plus 1, you plug in n plus 1 in for n, so you're going to have to distribute that 2 to the n plus 1. So don't just make it x to the 2n plus 2. That's not right. Okay. So simplifying, we should get negative 1 to the n plus 1, x to the 2n plus 3, times 2n plus 1 factorial, all over 2n plus 3 factorial, times negative 1 to the n, x to the 2n plus 1. Now let's cancel. Negative 1 to the n, negative 1 to the n plus 1 cancel, the x's cancel, and the factorials cancel, leaving 2n plus 3 times 2n plus 2 in the denominator. Limit as n goes to infinity of negative 1 x squared over 2n plus 3 times 2n plus 2. Okay. This is always going to be 0, which is always less than 1, because the degree of the denominator of n's, or the degree of the exponents in the denominator, is bigger than the degree of the exponents in the numerator for n's. So since the degree of the n's in the denominator is bigger, it's going to converge to 0, which is less than 1, which means that the interval of convergence is infinity, and the radius of convergence is infinity as well. Okay, example 3. Do ratio test first. Cancel things out. So we have n plus 1 times x minus 3. We're finding the limit of that. Now the numerator is always going to be bigger, so it's always going to be infinity, which is always greater than 0. But there is one value of this function that would make the limit not be infinity, and that value is 3. Oh shoot, I gotta go back. That value is 3, because if 3 goes in for x, then that limit equals 0, and so it's always going to be 0 is always going to be less than 1, so it will converge only if x is 3. You have radius of convergence of 0. Okay, that's radius and interval of convergence. The next thing we're going to go to is recognizing a power series in function notation. Okay, if you notice, a1 is 2, r is 1/3, and the sum, you can rewrite that as the sum from 1 to infinity, 2 times 1/3 to the n minus 1 equals 2 over 1 minus 1/3. So if a equals 1 and r equals x, we can also rewrite this function as 1 times x to the n over, or 1 minus x. 1 over 1 minus x, sorry. This is also called a power series for this function. So let's do an example. If f of x is 1 over 1 minus x squared, let's write a power series for this function. Centered at 0 to make it easier. Well, our a1 will be 1. Our r is going to be x squared. So our sum will be n equals 1 to infinity of 1 times x squared to the nth. Find the interval of convergence. Well, remember, on a geometric series, the interval of convergence is when the absolute value of r is less than 1. So x squared should be in between -1 and 1, which also means that x should be in between -1 and 1. Okay, example 2. Let's let f of x equal 1 over x plus 4. Let's find a power series. Let's keep it centered at 0 for now. Remember, the formula for a geometric power series is a1 over 1 minus r. So a1 is, we're going to have to rewrite it. If we have 1 over x plus 4, we want to put the 4 in the front. 1 over 4 plus x, and then somehow I want to make that 4 a 1. So I'm going to divide everything by 4, the numerator and all the denominators, or components of the denominator. So 4 divided by 4 is 1, and x divided by 4 leaves you x over 4. Which means your a1 will be 1/4, and your r will be negative x over 4. So your power series will be from 1 to infinity of 1/4 times negative x over 4 to the n minus 1. And our interval of convergence will be when x over 4 is in between -1 and 1. So x should be in between -4 and 4. Last example. Let's say I give you a power series or a function that looks like this, and it says write a power series for this. But let's say I want it centered at x equals 4 this time. So what's different about this is I want to put x minus 4 into 4x. Now, if I do that, I can't just stick an x minus 4 in. So think about completing the square. When you put in a -4, and it's multiplied by 2 on the outside, really what I'm putting in is a -8, so I need to add 8 on the outside. So 15 over 2 parentheses x minus 4 plus 7 should be equivalent to 2x minus 1 in the denominator when you simplify it. And then we'll put the 7 in the front, 7 plus 2x minus 4. And then we'll make the 7 a 1, 15 over 7, 1 plus 2/7 x minus 4. So our a1 is 15 over 7. Our r is negative 2/7 x minus 4. So our power series will be 15 over 7 parentheses 2 over 7 x minus 4 all to the n minus 1. Done. We've created a power series centered at x equals 4. Okay, homework is on Blackboard for these 2 parts. Try to do them for next class, and I will see you later. Bye.